Okay, in this video we're going to be looking at logarithms. First, let's think about exponential functions. Logarithms are just the inverses of exponentials. So consider this basic logarithm or exponential function here with a equals 1. Our initial amount is 1. And some base that's bigger than 1, so we have exponential growth, just as an example. This is a one-to-one function. One-to-one functions have inverses. So this guy has an inverse. An inverse. So let's try to find it. We would do y equals b to the x. First step in finding an inverse, replace y with f of x, or replace f of x with y. Next step is swap out x and y. So we would swap and get x equals b to the y power. And then we would solve for y. Okay, so you go ahead and pause the video. You go ahead and solve that for y. I'm giving you a chance here. Okay, you couldn't do it. No matter what you tried here, you can't get this y by itself. But we know this inverse exists because this is a one-to-one function. We know it has to have an inverse. So we're just going to define the inverse, define this new function where we say y equals log base b of x means b raised to the y power equals x. So that's the definition of this object here. When I say log base b of x equals y, that means I'm looking for some y value so that b raised to that y would have been x. These say exactly the same information. We call this log form. And we call this exponential form of the same information. So the inverse of this exponential, f inverse of x, is log base b of x. So just like b in my exponential was my base, over here b is the base of the logarithm. So if this were 3 to the x, this would be log base 3 of x. Focus seems a little off there. Okay, so this exponential function has a graph that looks like this. This guy here had a domain, all real numbers, had a range, 0 to infinity, and had a horizontal asymptote at y equals 0. His inverse, remember when you're going from a function to his inverse, domain and range switch, all the x's and y's switch. This guy passes through the point 0, 1. So my inverse over here will pass through the point 1, 0. Instead of having a horizontal asymptote, we'll have a vertical asymptote. So here we get a vertical asymptote, x equals 0, instead of horizontal y equals 0. And we'll have a graph that is going up like this. This is the graph of log base b of x, where b is some base bigger than 1. We're going to switch our domain and range. The domain of a function is the range of his inverse. The range of a function is the domain of his inverse. Okay, so here's a function, here's his inverse, the logarithmic function. Okay, now something very important just happened here. We got a domain restriction. So you need to make a big note of it here. Big giant note. Domain restriction. You can never have log any base of 0 or log any base of a negative number. You can't do logs of 0, can't do logs of negatives because they're not in the domain of the function, because they're not in the range of the basic exponential. Okay, so let's kind of play around with logs for a minute. If I were to ask a question like, say, log base 2 of 8, what does that mean? That means I'm looking for the exponent. I'm asking 2 to what power equals 8. Logs are exponents. The answer to a log question is the missing exponent. Well, we know 2 to the third power would be 8. So log base 2 of 8 is 3 because 2 to the third power equals 8. 2 to the third equals 8. I like to think of it like a little circle. 2 raised to the power of 3 equals 8. Logs are exponents. The answer to a log question is the missing exponent, the power you would put on the base to get the input. Okay. So let's say we wanted, I don't know, log base 5 of 25 equals what? Some question mark. The question I'm asking is 5 raised to what power equals 25? 5 to what power, question mark, is 25? This is log form. This is exponential form of the same question. These are exactly the same question. And of course the answer is 2. Log base 5 of 25 is 2 because 5 squared is 25. So the answer to the log question, this side over here, is the missing exponent. This was exponential functions. I give you the 5 and say square it, you give me 25. The log is the inverse of that. I give you the 5, I give you the base, I tell you the answer is 25, you work backwards and you give me the exponent. Exponential, logarithmic. Okay, let's play with evaluating these a bit. Okay, so say I wanted, I don't know, log base 3 of 27. The question is, what power do you put on 3 to get 27? I'm not dividing. Nothing is divided here. It's not 27 divided by 3. It's what power do you put on 3 to get 27? And the answer is 3. Because 3 cubed is 27. Okay, here's a tricky one. What if I said log base 4 of 2? That's not 4 squared. This is the base. That's the answer. I'm looking for the missing exponent. It's not 2. You might think, oh, 2. No, 4 squared is 16. That didn't work. I want to take 4 to some power and get 2. What operation could I do to 4 to get 2? I know square root of 4 is 2. But wait a minute. Square root, that can be written as an exponent. That's 4 to the 1/2 power. 4 to the 1/2 power is 2. Square root of 4. So the answer here is 1/2. Similarly, log base 25 of 5 is 1/2. Because 25 to the 1/2 power base raised to the exponent equals what's inside. 25 to the 1/2 power means square root of 25, which is just 5. Okay, let's take it up a notch. What if I wanted log base 3 of 1/3? What power would I put on 3 to get 1/3? That's -1. What? Yes, 3 to the -1 power. Negative exponent just means flip it over. That's 1/3. Here's log form. This is exponential form. These two things say exactly the same thing. But wait a minute. You just said logs can't be negative. No, I didn't. I said the inside can't be negative. You can't have a negative here. The answer can be negative. Remember, our range is all real numbers. The answer can be anything. It's the inside that can't be negative or 0. Can't have a negative or 0 here. I could easily have a negative or 0 over here. Okay, let's keep going. What if I wanted log base 2 of 1/8? Well, how do you get from 2 to 8? You cube it. How do you get it down in the bottom? You make it negative. That would be -3, because 2 to the -3 power would be 1/8. Okay, what if I wanted log base 6 of 1? What power would we put on 6 so that the answer is 1? The answer is 0. The exponent would be 0, because anything that's not 0 raised to the 0 power is 1. Okay, what if I had log base 2 of -4? That's a -4 right there. What power would you put on 2 to get -4? You can try all day. You ain't going to get anything. That does not exist. You can't do it. You can't take logs of negatives. 2 to some power will never equal a negative because the range of the exponential doesn't include negatives. Similarly, log base 7 of 0 does not exist. You can't take log of negatives or 0. Okay, properties of logs. These are the rules of logs. These you have to have memorized. There's no getting around it. You have to memorize these and know how to use them. First rule, log base b of b equals 1. A couple of different ways to think of this. One is just convert to exponential form. B raised to the first power does in fact equal b. So log base b of b equals 1. Another way to think of it is understand what logs mean. I'm asking here, what power would I put on b so that I just get b? And the answer is 1. Okay, log base b of 1. No matter what your base is, log of 1 always equals 0. Why? Because anything to the 0 power is 1, as long as your base is not 0, and we're not allowed to have 0 as a base. So log any base of 1 always equals 0. Log base b of b to the x is just x. I'm going to prove this 3 different ways. First off, converting to exponential form. B base raised to this exponent is supposed to equal what's inside. A little circle here. B raised to the x equals b to the x. Okay. Another way to think of this exponential function and this logarithmic function are inverses of each other. That's the entire point of this video. Logs are inverses of exponentials. If you have inverses, they cancel each other out, leaving behind just x. And then I'll use Rule 6 in a minute to prove Rule 3 again. Okay, these three you just have to believe me on. I'm not going to prove these three. It's a lot of work to prove them. It's in your book if you want to look it up. Log base b of m times n. Just think about rules of exponents. If you multiply like bases, you add the exponents. Well, logs are exponents, so multiplied inside becomes added outside. Divided inside, log base b of m divided by n is log of m minus log of n. Divided inside becomes subtracted outside. That's just rules of exponents. And rule number 6, again, rules of exponents. When you raise a power to a power, you multiply. If you have log of something raised to a power, this exponent can come down in front and multiply the expression. Okay. For fun, I'm going to use number 6 to prove 3. Again, for the third time. Okay, so rule number 3 says log base b of b to the x. By rule 6, I can take that exponent and bring it down on ground level with everybody else. So I get x times log base b of b, but log base b of b by rule number 1 is just 1. I get x times 1, which is just x. So a third proof showing kind of all the rules go together. Okay, expanding logs. So somebody might hand us something that looks like, say, I don't know, log base 3 of x times y. And they want me to write this as a sum or difference of logs. Well, using the product rule, multiplied inside would become added outside. That would be log base 3 plus log base 3 of x plus log base 3 of y. I'm done. Okay, let's make it a little more challenging. What if we had log base 7 of x squared y to the 5th? Okay, using the product rule, I got a couple of things multiplied. Multiplied inside becomes added, 2 separate logs outside. Then I can use rule number 6 to bring these powers down and get 2 log base 7 of x plus 5 log base 7 of y. So all the powers come down front. Okay, stick it up a notch. What if I had log base 4 x to the 9th, y to the 11th, over z to the 4th, k to the 12th. Okay, now you can go through this, try it on your own. Go through this one step at a time, but you're going to see pretty quickly that all these powers are going to come down. Everybody on top is going to be added. Everybody on the bottom is going to be subtracted. So we're just going to expand this out. We're going to have 4 different logs here. Log base 4. I'm going to get an x to the 9th plus a y to the 11th. I'm going to go ahead and bring that 9 out and make this 9 log base 4 of x. Same with the y, 11 log base 4 of y. The powers come down front. The guys on top get to stay positive. The ones on the bottom end up negative. 4 of z minus 12 log base 4 of, who was our last guy? K. Anybody on top stays positive. Anybody on the bottom becomes negative. All the powers come down. We get a bunch of pluses and minuses. Okay, this is good practice. In the real world, what we usually end up doing, though, is contracting logs, going from stuff that looks like this back to stuff that looks like this. So let's practice that. our directions will say take whatever you're given and write it as a single log. So say I'm given log base 3 of x plus log base 3 of y. Added outside becomes multiplied inside. The sum of two different logs becomes a single log. That's my goal with single log, where these things that were added outside become multiplied inside. All right, what if I had 4 log base 7 of x plus 2 log base 7 of y minus 5 log base 7 of z. Okay, well, we know we could bring this 4 in. Anything multiplied outside becomes an exponent inside. So I would get x to the 4th, I would get a y squared, I would get a z to the 5th. And just remember, anybody that's positive is on top, anybody negative is on the bottom. So I could just jump right to the answer here. Log base 7. I'm going to get an x to the 4th, a y squared, and a bottom of z to the 5th because that z was negative. Anybody that's negative just ends up in the bottom. Okay, what if I had log base 2 of x minus 1 plus log base 2 of x plus 1? I've got two things, same base. It has to be the same base or we can't do this. Added outside, we'll get multiplied inside. We'll get log base 2 of x minus 1, x plus 1. And then if we wanted to, which we will at some point in the future, we could go ahead and FOIL this out and say that's log base 2. You can check this on your own. That's x squared minus 1. Okay. Added outside becomes multiplied inside. Okay. We need to talk about natural logs and the natural number e. So we've got this very special number. He's kind of like pi. He's actually kind of related to pi. It's called Euler's number, if you're curious, or Euler's constant. It's a special number in mathematics. It's called e, and it's what you get if you take this expression and you plug in bigger and bigger and bigger values of n. You plug in n equals 100, n equals 1,000, n equals 1,000,000,000, and you keep going on forever. You do this concept called a limit. Take the limit as n goes to infinity, and this value here levels off at this irrational number that's approximately 2.718. This goes on forever, but it is finite. It's less than 3. This makes a perfectly good base for exponential functions. I could say the natural exponential function is f of x equals some initial amount times e to the x. Makes a beautiful exponential function. It's got a base that's bigger than 1, so we get exponential growth. Physicists, biologists, chemists, we all love the natural exponential function. He's got a buddy that goes with him called the natural logarithmic function, or the natural log. So it would be his inverse. We'll just call him, say here, g of x equals log base e of x. Okay, now back in the day when logs were first developed, typing this out on an old typewriter, an old printing press, we didn't have typewriters, was a real pain to get that little subscript there. So everybody got together and agreed, look, let's shorten this guy so we don't have to type this little base here. And let's just call this ln of x. That's natural log. It's from the French. They would say logarithm naturel of x. So that's why it's ln instead of nl. But this, when you see this, this means you've just got a log function and your base is e. And another common thing people would do back in the day, we liked a lot of different log functions. The most common one people use would be log base 10 of x. And again, for the same reason, because it was hard to write that on a printing press, we would just write log of x. So anytime you see log of x or log with no base written, you're supposed to assume this is the common log. Common log, and the base is 10. ln, base is e. Log with no base written, base is 10. Okay, now I really like these problems. These are really good problems for understanding properties of logs. Suppose I give a name to natural log of 2. So you could type it in your calculator. It's some nasty decimal. Natural log of 3. I give it a name. I call this guy u. I call this guy v. I know there's some nasty decimals. We're not going to use the calculator here. I want to write these expressions using only u's and v's. No logs in my answer. Okay, so for example, let's start with number 2 here. Natural log of 6. Well, I know 6 is 2 times 3. 6 is 2 times 3. By the rules of logs, multiplied inside becomes added outside. Natural log of 2 times 3 is natural log of 2 plus natural log of 3. Multiplied inside is added outside. But wait a minute, I gave that guy a name. Natural log of 2, I called u. And natural log of 3, I called v. So natural log of 6 is just u plus v. That's the game we're playing. I want to write each of these using 2's and 3's, maybe with some exponents and so forth. Okay, so 16. I want to think either a bunch of 2's and 3's multiplied together, or maybe just some 2's, maybe just some 3's. Well, 16 is 2 to the 4th power. Okay, now I have to use my rules of logs. An exponent inside can come down on ground level. So natural log of 2 to the 4th is 4 times ln of 2, but ln of 2 has a name. I called it u. So that's what I'm looking for u. Natural log of 9/4. First off, divided inside is subtracted outside. ln of 9/4 is ln of 9 minus ln of 4. Now I have to think, how can I get a 9 using powers of 2's or powers of 3's? Well, 9 is just 3 squared. Same with 4. 4 happens to be 2 squared. Nothing special that they're both squared. It's just a coincidence. I can bring both of those exponents down. Exponents inside become multiplied outside. That's a 3 right there. Natural log of 3 was what we called v. So I get a 2v minus natural log of 4 I called, oh, that's a 2. Let's fix that right now. That's a 2. 4 is 2 squared. 4 is not 4 squared. 4 is 2 squared. So natural log of 2, we called u, so we get a 2u here. Okay, what about natural log of 12? I want to write this as some 2's, 3's multiplied together. We got a bunch of choices here. You might think, I'm going to do it a couple of different ways. Well, 12 is 3 times 4. So natural log of 3 times 4. Multiplied inside becomes added outside. Natural log of 3 I got a name for. He's v. 4 here, I got to play the same game I did over here. 4 is 2 squared. I don't know natural log of 2 squared. I just know natural log of 2. So I need to get this 2 down to ground level. Okay, natural log of 3 we named v. Natural log of 2 we named u. So we get v plus twice u. But wait a minute, you're thinking, hold on. What if instead I said 12 is 2 times 6? Okay. Then that would be ln of 2 plus ln of 6. We've already done ln of 6. It's right here. ln of 6 was u plus v. ln of 2 is another u, so I get a u plus a u plus v, which is a twice u plus a v. Same thing. Are those the same? The order's different. Yes, of course they're the same. Addition is commutative. Okay, that is logs. I will put a link here. Right now it should be popping up to click on exponentials, solving exponential equations, and solving logarithmic equations.